Dear students, in today's video lecture we will deal with the basic 3D transformations. Until now, what we had been doing was in two directions only. These two standard directions were horizontal called X and the other one was vertical called Y. So every measurement and every transformation was taking place in these two directions only, keeping all the things contained in a two-dimensional plane, that is the screen of your monitor, and every point was measured in a two coordinate system, x and y. Actually, what does this meant? X was the first coordinate, x was the distance, horizontal distance from origin, so this distance, and similarly y was the vertical distance from the origin. So a point P having coordinates xy meant you start from the origin, move x units in horizontal direction and then y units in vertical direction, you will reach this point. But now onwards we will move from two-dimensional to three-dimensional. It's not that difficult. Only an additional direction is added to system now. This direction called Z is perpendicular to the plane. You can well imagine it. This direction cannot be depicted on the monitor. Therefore, special effects are used to indicate it is drawn in a slant direction, indicating that it is neither horizontal nor vertical direction. So this direction actually is the direction moving outward from the screen towards you. This is the positive direction of Z in the Z positive movement along Z direction, and if you move inward to the screen, it is negative Z direction. So our point will now change from xy to xyz. It will have three coordinates now x and y as usual, and the z coordinate in the third dimension. So now we will discuss the transformations, basic transformations one by one. First of all, let us take up 3D translation. So a picture depicting 3D translation is in front of you. Here this is an object, three-dimensional object, and it is moved from this to this. In this system you have x, y and z, three standard directions, and when you are to move an object from one place to another place, you take the same basic principle. You divide the object into defining points. Let us take this defining point as an example. Suppose xyz are the coordinates of the original position of the object. Suppose this object is moved from this to this and the corresponding point is moved from here to here. So x dash, y dash, z dash are the coordinates of the new location of this point, and we have to calculate these coordinate values. This is quite simple, as we did in two-dimensional system. X dash was calculated by adding tx, which is the translation parameter along x-axis, adding this parameter to x value. So x dash is equal to x plus tx. Similarly, y dash was calculated by adding translation factor along y-axis, ty to y coordinate. We just extend the two coordinate system into three coordinate system. Z dash, on the same pattern we get the third equation, z dash is equal to z plus tz, where tz is the translation factor along z direction. So using these equations, these three equations, we can find out new values of the coordinate of the point x dash, y dash and z dash, and of course all the defining points will be applied the same transformation. The same thing can be done in matrix form like this. We had this matrix tx ty, 2 by 1 matrix, 2 rows and 1 column. matrix for 2D translation. If we extend it to 3-dimensional, we will get the similar matrix, but it will be a 3 by 1 column matrix. So additional translation factor TZ will be included here. But if you remember, we used to have homogenized form of the matrices to solve so many problems. First of all of the matrices are of the multiplicative nature, and secondly, all of them having the same dimension 3 by 3. So homogenized form of 2D translation was this. And similarly, on the same pattern, we extend this to 3-dimensional system. In this, we have homogenized form of the matrix, which is 4 by 4 matrix. These values are Tx, Ty and Tz as usual, translation factor along x, y and z directions, and all the 4 diagonal elements. This time we are having 4 diagonal elements, earlier we had 3. 4 diagonal elements are set to 1, and the remaining non-diagonal elements will be set to 0. So this is the matrix form, homogenized matrix form of 3D translation. And if we have to represent it in the equation form, it can be done like this. First of all, another change is here, a point matrix. Earlier we had xy1, this time we have xyz1, 4 by 1 matrix. So this is point matrix, and this is the translation matrix, and translation matrix multiplied with the point matrix gives you the point matrix for the new location x dash y dash z dash 1. If you multiply these matrices, you will get the same set of equation, x dash is equal to x plus dx and so on. So when you are to solve the numericals, you prefer to have matrix form, otherwise you can have equation form also. Let's now move on to the rotation, 3D rotation. Here we have a number of changes. First of all, if you remember, rotation in 2 dimension was taken about a point. Rotation was mentioned about a point, but in 3-dimensional system, rotation is not about a point, it is about a line instead. So rotation about a line, for example, you are having this line in the horizontal direction, and the rotation about this line will be like this. If you change this direction, let us suppose direction in y-axis, the rotation also changes its style, and similarly we can change the line along the z-axis, then rotation will be different altogether. Better picture version of this is given here. So this kind of rotation is known as rotation about x-axis. This is rotation about y-axis, and this is rotation about z-axis. So let's take them up one by one. First of all, we take rotation about z-axis. So rotation about z-axis, if you watch it clearly, it is nothing different from the 2-dimensional rotation. So this rotation about z-axis will be specified by this set of equations. In case of 2-dimensional rotation, you had x dash and y dash equations of this form. We will have the same equations, and the third extension equation is z dash is equal to z, means z is unchanged. Only x and y coordinates change according to these equations. So x and y are the xy coordinates of the original position, and theta is the angle. Here I have taken the sign of phi by mistake. So this is the angle through which rotation is to be made. Here one point I want to mention, the rotation about rotation in the anti-clockwise direction is taken positive angle, and the rotation taken in the clockwise direction will be taken negative, as negative angle. So this is the set of equation. This set of equation specifies new location after rotation about z-axis. Similarly, we have rotation about x-axis now. We have this set of equations. In this system, x changes, x does not change, x remains unchanged, x dash is equal to x, and y dash and z dash are calculated using these equations. Similarly, rotation about y-axis, we have this set of equations. In this system, y remains unchanged, y coordinate is not changed at all, z and x are changed, and the change is found using these equations. An easy trick to remember these sets of equations is this. You simply have the set of equation about z-axis. You can use them to find out these two remaining sets by simply replacing x with y everywhere. Wherever x exists, if it is x dash, it will be changed to y dash. If it is x, then it will be changed to y. Similarly, y will be changed to z, and z again will be changed to x. For example, from this set of equations, all the values will be changed. So this z will be changed with x. So you get rotation about x-axis. X will become y. X dash will become y dash. X will become y, and y will become z. Similarly, y dash will become z dash. X will become y. Y will become z, and z dash will become x dash. Z will become x. So you get this equation, set of equations. Now again, if you make the replacement to this set, you will get this. So x will be replaced with y, so you will get rotation about y-axis. Similarly, y dash will become z dash, and z dash will become x dash, and x dash will become y dash. So an easy trick, a trick to remember them easily. So the same thing can be done in matrix form in this way. So these are the matrices of rotation. This is rotation around z-axis. This is the equation, 4x4 equation, homogenized equation in 3D system. This is point matrix. This is point matrix for the new location. Here W should be 1. It is by mistake W here. Similarly, rotation about y-axis is having this equation, this matrix. Similarly, rotation about x-axis is given by this matrix. You better remember them so that numericals can be solved easily in exams. Third rotation, basic rotation, is scaling. So scaling will take place like this. Object, original position, and it will be scaled up or scaled down. If it is scaling factor is greater than 1, it will be scaled up, and if it is less than 1, it will be scaled down. It will be reduced in size, I mean. So equations for finding new value, new location, new point are x dash is equal to sx, where sx is the scaling parameter along x-axis, and this will be multiplied with the x coordinate. Similarly, y dash will be calculated by multiplying, it should be y here, not x, scaling factor sy multiplied by y. Similarly, z dash is equal to scaling factor along z-axis multiplied by z. So x dash, y dash, and z dash, new values of the coordinate, can be calculated using these equations, and the same thing can be done in matrix form like this. It's not okay. It should be sx, sy, sz, 1, 0, 0, 0. Here it is wrong. So This is translation matrix. So I repeat, this should be Sx scaling factor along x-axis, this one Sx, and this should be Sy scaling factor along y-axis, and this should be Sz scaling factor along z-axis. These values will be 0 and this will be 1. So the scaling matrix for homogenized matrix for scaling in 3 dimension will be like this. So please make this amendment before trying. Hope you understand these basic equations. So now these basic equations can be made use in the composite transformations, as we had done in the 2-dimensional composite transformations. Multiple matrices will be arranged in proper order, then they will be multiplied and a single resultant matrix will be known. So thank you very much.